Well, good morning, everyone. It's a great pleasure and honor for me to introduce our speaker for the next mini course, Akihiro Munemasa. So we know each other, I don't know, at least for 30, almost 30 years.
Almost 30 years.
Yeah, so I said that Akihiro got his undergraduate degree from Sophia University in Tokyo, got his PhD at the higher state university, supervised by Professor Hanai. And then after that, he returned to Japan. I think this was the time where was the Congress, and then Akihiro and Tsurugi, there was an unforgettable trip to on the train. At that time, Akihiro was at Kyoto University.
Osaka.
Osaka.
Yes, Osaka. Yeah, also Tatsuro.
When I first came to Osaka, Kyoto University, there was something written by Chong at the bottom of the office of Tatsuro in Japanese. So I was wondering, what was this? And that Tatsuro translated it. It's written, the door is stuck. So keep exactly here to open. But then after that, in '94, Akihiro moved to Tohoku University.
No, 91 to Kyushu.
To Kyushu University, sorry. Yes, right. In '94,
2003 to
Tohoku.
Yes.
2003. Yeah, sorry. 2003 to Tohoku University, where he is currently a professor. So he published almost 50 research papers on various aspects of geometry, combinatorics, coordinate theory, and for me it was exciting result on triply even chord, which I think built a bridge between combinatorics and various accommodated algebra. So he is editor of Journal of Graphs and Combinatorics, and one of the chief journal
algebraic combinatorics.
Algebraic combinatorics, very dedicated and strict editor of this. And now I guess he will give us a talk on permutation, representation of finite group and association.
Yeah. Thank you very much for a very nice introduction. It reminded me of this unforgettable trip in Japan when Sasha first came to Japan, and this night train and sleeping car. It was. I now have experienced this here in Russia. I mean, the night trains are isomorphic. Yeah. We have beds, 2 beds, and 4 persons in compartment. Okay. Now, these lectures are meant for beginners, so it's not for experts like Sasha or many of you who already know permutation groups and even association scheme, and probably it's quite boring in the beginning. So you are welcome to, it's a little bit strange, unwelcome to stay, or rather welcome to leave, or welcome to do whatever you want if you think the material is too easy. So, but there are students, and also I will have a problem-solving session tonight, so I will give sufficient background. during these two lectures. So in particular, at the end of the second lecture, I will give a detailed description of the goal of the problem-solving session that is about the two interesting inequivalent permutation representation of the Matthew group. You don't have to know anything about Matthew group. I will explain the properties which are necessary to solve the problems. So the first lecture is mainly to serve as the introduction and also the definition and notation, which are commonly used not only in my lecture but also Misha Mutich's. We had a meeting with Misha yesterday to check our slides, and we try to unify our notation. So most notations are similar. Also, the topics are similar. The only difference is that I will mainly focus on association scheme and also permutation groups. And Misha will focus on coherent configuration, which are more general objects than association schemes. So here are the contents of the 8 lectures. So the first lecture is just a notation and also about motivation. And the second lecture is a basic introduction to association schemes. So the first and second lecture are very, very basic introduction to permutation groups and association schemes, also very boring for experts. And the third lecture, I will develop a basic theory of star algebra over complex number field. Edwin van Dam mentioned star algebra in the context of semi-definite programming. So this star algebra is just the same as his star algebra. Instead of developing a more general and abstract theory about semi-simple algebra, I will restrict myself to star algebra. Then that is easier to work with, and the examples are more concrete. And then in the fourth lecture, I will develop a theory of commutative association scheme and eigenmatrices and crime theorem. These are all standard topics in commutative association scheme. And then one of the main examples of the commutative association scheme is the center of the group algebra, and then the eigenmatrices are essentially the same as the so-called the character table of the finite group. And then in the sixth lecture, I will actually prove a formula due to Charles Curtis and Robert Fossum about the formula for the central idempotence in the centralized algebra. And then I will use this formula to deduce the eigenmatrices can be expressed in terms of roots of unity. And so that introduced the concept of splitting field. And I will mention my old results about the splitting field that is from 1991. And then in the final lecture, I will mention application, but at this point, it's not so clear what application would mention. Maybe I may not have much time to do that 8th lecture, but if I have time, I'll try to mention how to compute eigenmatrices. Okay, so that's all. So you know exactly what I will be talking, so you can plan which one you focus and which one you will skip. Okay, so very we start at the very beginning, a permutation group. I noticed that even the word permutation group, the definition differs from discipline to discipline. Within mathematics, the topologists sometimes define permutation group to be just the symmetric group. But of course, for us, a permutation group is not only a symmetric group, but any subgroup of a permutation group, so subgroup of the symmetric group. So the notation for the symmetric group is sim of omega, where omega is a finite set. You could consider omega to be arbitrary, say, possibly infinite set, but I will not consider infinite permutation group. All groups are finite except the general linear group of a complex number. They are, of course, infinite. And more generally, I think Roman Nedela mentioned what the action is. And instead of considering just permutation group, I also it's more convenient to talk about action. That is, well, one could define it in a formal way, but for us it is enough to say that action is just a homomorphism from a group to a symmetric group. And the difference between these two is just the faithfulness. Faithfulness means just the injectivity of this homomorphism. So if the homomorphism is injective, you may identify the group G with its image, which is a permutation group. But we also allow non-injective action. So the action is more general. But then if the action is not faithful, then there is a kernel which does nothing on the, in terms of permutation on the set omega. The notation for the permutation is the standard among permutation group theorists. We write permutation from the right. So it is composed in a different way from the usual composition of mappings. So the omega is little omega is an element of set omega, and if G is an element of the permutation group, we denote the image of omega under G, like omega to the power G. So this exponential notation is used. So we multiply permutation from left to right, from right to left, as in the case of composition of mappings. And if G is a finite group and H is a subgroup, then you can create an action, so-called coset action, where G by H is the set of all cosets. You can consider coset in the other way. Say, here the set of cosets is Hx, but you could consider set of all cosets of the form Xh, but I will never do that, consider that. So G mod H, or G slash H, or G by H is the set of all cosets of the form Hx, so that we can let element of G act from the right by multiplication. So G is mapped to the element of the symmetric group of G over H by sending Hx to Hxg. So the G is mapped to the permutation which sends Hx to Hxg. And you could take H to be just the identity subgroup. Then the cosets are just singletons. You may think of them as a group itself, and that is called the right regular representation. But here we have a first encounter of the word representation. So what is a representation? Well, I already defined what right regular representation is, but there is no precise mathematical definition of the word representation unless you specify what mathematical object you consider, like group or algebra. But so I will not define the general term, but from specific to general, the right regular representation is, as I defined it, is an action of G on itself. So it is a homomorphism from G to the symmetric group. And more generally, a permutation representation G is nothing but the action. So it's just a homomorphism from G to some symmetric group, or some set omega. Second kind of representation is a matrix representation. So here the symmetric group is replaced by the general linear group. So this GL and F is the group of invertible elements of n by n over field F. So this is an infinite group if F is an infinite field. So this is a matrix representation, but the more generally you can just say a representation without any adjective. This is representation of a group G, which is a homomorphism into GL of V. This is a group of invertible linear transformation of some vector space V. So this is a general terminology for representation of a group. I will have a representation of algebra and also a representation of association scheme later, but here the representation is only for groups so far. So in general, there is no rigorous definition of the word representation, but the naive way to describe is the representation means it's a description using a typical object. Here we are in the category of groups. So typical objects in group, you may consider the symmetric group. Maybe that's one of the first example of group when you first learned group theory. And also another typical object is general linear group, a group of all invertible matrices. So so the representation means it is a description of an arbitrary object, so arbitrary group, in terms of a typical object called symmetric group or general linear group. Now, from here, I go back to the permutation group and explain basic concepts which are needed in later lectures. So if G omega is an action, then the G orbit is just simply the set of all image of an element omega. And a stabilizer is the subgroup consisting of all elements G, which fixes this particular element omega. Then there's a so-called orbit stabilizer relation that is the length of the orbit is in one-to-one, or is the same as the index of the stabilizer, because there is a one-to-one correspondence between elements in the orbits and the cosets, because every coset maps this element omega to one particular element, independent of the choice of element from the coset. So there is a one-to-one correspondence, so you have this relation. So for the coset action, it's clear that the stabilizer of a coset hx is x inverse hx, because if you multiply elements from x inverse x, then x will disappear. So this is precisely the stabilizer. So if you want to stabilize everything, that is, if you want to fix all the cosets, then you need to take the intersection of all stabilizer, and that is called the core of the group H, or the core of the subgroup H inside the group G. And it is obvious from the definition that this is a normal subgroup. And then next to if the orbit is entire omega, then we call it transitive. That is, if omega is little omega to the power G, well, it doesn't matter which particular small omega you take. Once you have such omega, then this is true for every other element omega in capital omega. Such an action is called transitive. And we have seen semi-regular action previous week. This was quite important in graph covering. Action is called semi-regular if a stabilizer of every element is just identity. And we call the action regular if it is transitive and semi-regular. we have seen regular action because we have defined right regular representation, and this terminology is consistent with this definition of regularity because right regular representation is regular because it's clear that the G acts transitively on G itself by right multiplication, and if you fix one element, then it has to be identity. Another action associated with the group is action by computation. This is not the right regular action, but you also multiply G inverse from the left. So if you pick an element G, then G acts on G itself by conjugation. So H is sent to G inverse HG. So the orbits of these actions are called conjugacy class, if you don't know. If you know, it's clear. So this action is not transitive, well, unless in the trivial, except in the trivial case, because the identity is fixed always. So the orbits are called conjugacy class, and this will play an important role in representation theory, especially in the investigation of the center of the group algebra. Now we need to define equivalence of two permutation representations, or two actions. So we consider two sets, omega and delta, but the same group acting on omega and delta. These two actions are said to be equivalent if there is a bijection between these two sets, omega and delta, which are compatible with this action. What does it mean for the bijection to be compatible? It means that this diagonal commute. So if you start with this upper left corner omega, then there are two ways to reach the lower right delta. First, you apply an element G to transform this element inside omega, and then use the mapping F to get the element in delta. You could instead first transfer that element to delta and then apply this same G, because G also acts on delta. So we require you produce the same element, no matter which G you take, and no matter which alpha you take from this set. So this is the compatibility, and if this is true, then we say omega and delta these two actions are equivalent. Then it's a standard exercise in the permutation group that transitive actions are equivalent to the right and the coset action. So if you take a transitive action, then you can speak about the stabilizer, and the stabilizer gives rise to a coset action, and these two actions are equivalent. So it means that every action is equivalent to some kind of disjoint union of coset action. If you consider arbitrary action, then it may not be transitive, but you can decompose into transitive part, and every transitive part is equivalent to coset action. So it is not necessary to consider all kinds of action, but it is sufficient to consider just transitive action and then coset action. So really, the theory of permutation group is just a pair of group G and stabilizer H, nothing more. Throughout the lecture, I will develop all my theories in terms of matrices. So it's important to understand everything in terms of matrices, including the permutation. So the main notation for the set of matrices is M omega of F, where F is a field, omega is a set which is used to index the rows and columns of a matrix. So if I have a permutation, I can construct a matrix this. It is either 1 or 0. 1 will occur at the position alpha beta, because the positions, matrix positions are indexed by elements of omega. Precisely, this alpha is mapped to beta under the mapping associated with group element G, and this is denoted by P sub G. Well, of course, this P sub G depends on the action, but it is always clear what the action we are talking about, so I will use PG to denote the permutation matrix associated to a group element G.
So, if I may allow to say, if you require some ordering on omega to turn it into matrix, you need some ordering. So,
yes. So, for the beginners, you may think of omega as a set consisting of 1 to n, but omega is an abstract set, so it's a little bit strange to use abstract sets as to index metrics. So, but yeah, intuitively you should index omega by, or you should give numbers, assign numbers to elements, and then you can turn the matrix indexed by omega to the matrix in the ordinary sense. But this numbering is not necessary to define the matrix product, because the matrix product, what you do is, if you have a matrix A, B, and what is the product? This is summation of gamma, omega of A, of alpha gamma, B of gamma. Okay. So this is the usual matrix product, and it is not necessary to number them, because it's just a summation of a set. So we will perform matrix multiplication just like the ordinary matrix, except that the difference is that the rows and columns are indexed by some abstract set and not the set of numbers from 1 to n. Yeah, so in the second case, I write GL size of omega. So for that purpose, I need the numbering of elements of omega. So in this way, the permutation can be considered as a matrix consisting of only 0 or 1, so it can be defined over any field. So this is called so this gives a matrix representation. So the permutation representation gives rise to a matrix representation always. But that is not trivial. You have to check, if you haven't seen this, but if you multiply 2, then this has to be GH. Yeah, using the definition of the permutation matrix, you can check this. So it means that the mapping from G to PG, from symmetric group to general linear group, is a homomorphism. So it gives a metric representation. So if you have a permutation group, you can compose the permutation representation with this matrix representation to get a metric representation of a group G. And that is also called a permutation representation. Yeah, here I ended my slide with the exclamation mark and the question mark, but the reason is that in learning mathematics, we sometimes abuse notation, and the reader or audience should be careful about abusing notation. So here is the explanation. Because I define the word permutation representation in 2 different ways. One is a homomorphism from G to symmetric omega, so that is the action. The other permutation representation is a representation in terms of permutation matrices. So the only difference is that the codomain of this homomorphism or target space or the range of the homomorphism, one is metric group, the other is the general linear group. But the correspondence is clear, so we call both mappings permutation representation. So the action gives a permutation representation that is from G to the symmetric group. But we also use the same word permutation representation for the homomorphisms from G to general linear group that is obtained by composing this mapping which assigns permutation to matrix. So it is a matrix representation, and you may think of this matrix as a linear transformation on the standard vector space, when it is a representation. Now, we have defined the equivalence of permutation groups, so we also need to define the equivalence of representations. So two representations are equivalent if there's an F linear isomorphism, that is the vector space isomorphism, which transforms one vector space to another, and again, this compatibility holds. So there are two ways to go from V to W here. First you apply this linear transformation and then isomorphism F, or you could apply isomorphism F first and then transform by G. And we require this holds for all G and for all element V in the vector space V. So that is the definition of equivalence of permutation, representation, or matrix representation. Now, having defined two kinds of equivalence, I want to compare them, because permutation representation can be thought of a matrix representation. So for matrix representation, I have defined a new equivalence. Then it's easy to check the one equivalence implied the other. That is, if I start with the equivalent permutation representation, that is the diagram on the left, then I get equivalent matrix representation on the right. But it's not so, there is some tricky point that you see the F is, now it becomes F star, the arrow is reversed. And I have two different permutation matrices, so I have to distinguish them by putting omega and delta to denote the permutation matrix associated with the same group element G, but acting on omega and delta. So in this diagram, the arrows are reversed, but so this F star is a linear isomorphism which is induced by the bijection from delta omega to delta. Well, in the obvious manner. Yeah, because the vectors whose coordinates are indexed by omega can be thought of a function from omega to F. So if you compose with a mapping omega to delta, it produces a mapping from F delta to F omega, because you start with delta. Because you start with omega and then use F to go to delta and then delta to F by this. So the composition with F produces this bijection. And that bijection can be used to give the equivalence of representation. So what you have to check is this identity. So you take an element U from F delta, so this is the beginning part of this diagram, and you apply this. First you go down by this permutation matrix, and you apply F star, and that's on the left-hand side. On the right-hand side, you will take the other path, but then you just compute the entry of this vector and compare them. They that they are equal, because the equality comes from the equivalence of the permutation representation. It's a little bit tricky because this, if you see here, it is first you apply G and later apply F star, but it looks as if it's a bit differently. But this is correct. This is not the mistake. You apply F first and then G later, but if you think a little bit carefully, then this is the right one. So what is the goal of the representation theory or permutation group? So given a finite group, we are interested in what kind of permutation representation it has. So one would like to know all permutation representations. Also, one would like to know all matrix representations. So they are, of course, different because the equivalence is only one-sided direction. So, and the one, as I mentioned, the arbitrary permutation group, the set can be decomposed into orbits. So the arbitrary permutation group can be thought of the permutation group of transitive ones. You reduce this to the classification transitive permutation group. So this is essentially this knowledge of all subgroup, or more precisely, the knowledge of all conjugacy classes of subgroups. The second is to classify all matrix representations. It is a little bit more difficult, but I will get to the point later. But the problem is that the equivalents are different. So the problem 1 cannot be reduced to problem 2 because of course we know permutation representation gives rise to metric representation, but having classified metric representation doesn't mean you classify permutation representation because the equivalents are different. So here is the example. I'm going to Sasha's favorite, but probably he will also want to make some comment later. There's a famous group discovered by Emile Mathieu in the very long time ago, 18th century. This Mathieu group M23, 17th, 19th century.
Not 18th.
No, 19th, sorry, 19th century. The Mathieu group M23 has two inequivalent representations, omega delta, which I will later explain. Those two sets have the same cardinality, 253, such that the corresponding metric representations are equivalent. But they are not equivalent as permutation groups. So, well, if you are familiar with permutation representation, it simply means that you have two non-conjugate subgroups. But this example shows that the knowledge of general representation theory is not sufficient to say detailed information about permutation group. I will give more information at the end of the second lecture because the verifying this statement is exactly the goal of the problem-solving session. So if you are interested in this example, then I encourage you to come to the problem session. So the goal of studying permutation group in this lecture, well, not the goal of the whole theory, but my goal in this lecture is to review the structure of the central right hand, the algebra of matrices. So PG, the permutation matrix, this is just a matrix, so you may think of this, the linear span, or the algebra generated by the permutation matrices. So this is a subalgebra of matrix algebra. In particular, if you take right regular representation, for this PG, then the PG, those permutation matrices are linearly independent, so therefore they form a basis of this algebra, and so you may think of this as a group algebra. So if you know the old representation, or if you know the structure of this algebra, then it is equivalent to the knowledge of all representation of finite group G. So it's important to understand the structure of this algebra generated by permutation matrices, which live inside the full matrix algebra. So in general, this was the result due to Molienne. Last week, Leonid Bakuch mentioned that this is due to mathematician who spent 40 years in Tomsk. The Molienne proved this theorem. So the structure of the group algebra is just a direct sum of full matrix algebra. So essentially, so this already reveals what the kind of representation the group G has. Because you just take one copy of this full matrix algebra, then you get a representation, and it turns out that is an irreducible representation. So if you have R copy in this direct sum, it means you have exactly R inequivalent irreducible representation. And once you know irreducible representation, then there's a theorem called a Maschke's theorem, but according to Bakuch, it is also proved by Molienne that the arbitrary representation is a direct sum of irreducible. So it is enough to understand irreducible representations. Now, I need to mention a few other things which are needed. Perhaps not in my lecture, but in Misha Music's lecture. There is one important concept concerning transitive action. A transitive action is said to be imprimitive if there is a non-trivial G invariant partition of omega. Otherwise, it is said to be primitive. Here, a partition is said to be trivial if it has only one part, that's really a trivial partition, and but all of the other trivial partitions, that it consists only of singletons. Of course, kind of trivial. All other partitions, except these two, are called non-trivial. So if G admits a non-trivial partition, then it's called it is called imprimitive, and such a partition is called system of imprimitivity, or just an imprimitivity system. And once you have a G invariant partition, then of course G acts on that system. So it gives rise to another permutation group on this system of imprimitivity. It's not difficult to describe a situation group theoretically in terms of coset action, because transitive action is equivalent to a coset action. You might as well assume from the beginning that you have a coset action. So if G acts on the coset of H, then the partition, and if K is a subgroup lying between G and H, then you automatically have a partition that is H cosets are grouped into K cosets, and that is precisely invariant partition. In fact, every G invariant partition arises in this way, and that is a system of imprimitivity. So it means that the primitive permutation groups are equivalent to those permutation groups which has no K between G and the stabilizer. In other words, H is maximal sum. So that's an equivalence between primitive permutation group and the maximal stabilizer. Okay. Another way to produce an action is that the product action. So if you have two permuted actions of the same permutation group, then you may let G to act on the direct product. So if you have alpha beta on the direct product, you just apply G on each component, you get the permutation group. So in particular, if you take delta to be just omega, then G acts on the Cartesian power, second power, omega squared, and then it will not be transitive anymore. So you have orbit decomposition, and these orbits are called two orbits because this is omega squared, and or some people call orbitals of the group G. So the set of two orbits will be denoted by omega squared slash G. And because this is a subset of the direct product of omega with itself, you may think of this as a graph, or you may describe it in terms of square matrix called adjacency matrix. So you can just put 1 whenever you have an element alpha beta. So it is almost like a permutation group, except that the permutation group you have just a single 1 on every row and every column, but this adjacency matrix may have several 1s on row and column. So whenever you have a subset of omega squared, you get an adjacency matrix. So in particular, for the right regular action, omega is really G itself. Then you have two orbits of the right regular action. And if you compute what the two orbits are, then it turns out that it is almost same as the permutation matrix, but slightly different. This alpha beta and G1, G2 must be in the same relation R, but that is the same as applying, because it's a right regular representation, we apply something from the right. But if you apply something from the right, and then you make this product, that something goes away, so it will be the same for alpha beta and G1, G2. And if you express this in terms of Kronecker delta, you get this. This is almost same as the definition of permutation group, but it's different because this is a general permutation definition of permutation matrices, but for the right regular action, it's like this. But that is, the group element is on the left. So we call that the left regular action. So if you start with the right regular action, then these two orbits are not the same, but instead they are left regular action. So this fact is already mentioned, if you remember, it occurred already in the Roman Nedeller's talk. So this is the last slide, I think. So what I proved there, well, what I haven't proved, maybe I should prove this here now, but the proof consists only just manipulating formula, so I will not do that. So if you have an action, and if you have an R, which is two orbits, then the adjacency matrix of the two orbits R and the permutation matrix commute. You just compute the alpha beta entry, because the permutation matrix is expressed by Kronecker delta, it is pretty easy to find what the entry equals are, and you find to entry, it looks a bit different, but if you think of the fact that these relations are G invariant, so this is G inverse. If you apply G on both coordinates at the same time, you get this. So these two entries are the same because R is invariant under G. So this is the main feature of these two orbits. So that is the relations defined by two orbits, and the adjacency matrix defined by that relation is commutative. It commutes with the permutation matrix. So in the next lecture, I will axiomize this property of these two orbits and to define association scheme. Okay. So that's so.
Thank you very much. There are some questions, comments. I have some questions. First, I think we not quite agree with this. That you are trying to say that when you multiply, you sort of hiding the order.
Yeah.
But, well, this is not. So you know how to calculate alpha beta, but you have to know where to place it into matrix, that you need an order. This is one. And then the other, if you would show the slide where you have this correspondence between permutation, isomorphism, and matrix, can you slide it down?
The two diagrams.
Yeah. So I think that's the whole problem you're having, that you switch from left action to right action. You see, your F is from the left, and G is from the right. That's why you have to, but I think, well, in reality, there is no need to have two actions. So you have omega to delta, and then you take f of omega. You take omega as a basis, and then you have this mapping from omega to delta, and then extend it to linearly. So I don't think you really need this star. That's what I would say. Maybe it's just common that if you have a function, then if you have a vector space, you always act from the left.
That's what that's the convention I'm going to use. For vector space, for me, the linear transformation always act from the left.
Yeah, so in this way, you see this difference between F and F star is just because you want to switch from left action to the right. Okay, thank you. Thank you.